We will calculate the center of mass of a half a ring with a radius r. We consider a small segment along the ring with a length dl and mass dm. It has the shape of a circular arc and an angle theta with a positive x direction and subtends an angle d theta. Its position is given by the two coordinates x and y. The position of the center of mass of the ring along the x direction then will be equal to 1 over m integral of dm x. This is simply the definition of the center of mass for continuous objects. Due to the symmetry of the ring, we immediately see that the value of that integral is 0. This is not the case, however, for the vertical position of the ring. So we write that the vertical position is equal to 1 over m integral of dm times the vertical position of each of those segments y. We introduce the linear mass density as the mass per unit length. Lambda is equal to dm over dl. For a uniform ring, that also has to be equal to the total mass of the ring over the total length of the ring. Or we can also write that dm, in this case, can be written as lambda dl. We also note that if we work in radians that are defined as the length of the arc over the radius, we can write for the angle d theta that is equal to dl over r. Or, in terms of dl, dl will be equal to r d theta. With the two expressions for the mass of that little segment dm and the length of the segment dl, we go back to the integral for the vertical position of the center of mass of the ring, 1 over m integral of dm y. We replace dm with lambda dl, and we also replace dl with r d theta. And so eventually the integral becomes lambda r over m integral of y d theta. Let's go back to that linear mass density for a little bit. Lambda must be equal to the total mass over the total length of the ring for a uniform ring. In this case, the length of the ring is simply pi r, half the circumference of a circular ring. Rearranging the terms, we see that lambda r over m has the value of 1 over pi, and we also know that y, the vertical position of the segment, is equal to r sine theta. With the two expressions, the integral for the vertical position becomes lambda r over m integral of y d theta is equal to 1 over pi integral of y d theta, or 1 over pi integral of r sine theta d theta. Our integral is over the angle theta, so we can actually put the limits 0 to pi. The value of that integral is r over pi of minus cosine theta, evaluated at the two limits 0 and pi. The final value for the integral is r over pi times 2, and so the vertical position of the center of mass of a half a ring is 2r, the radius of the ring, over pi.